ready to go to lunchtime. So stay with us. Okay. Our presentation will be the speed of light through gelatin.
My name is Taylor Bishop.
I'm Joe Friday.
I'm Eddie Ibarra,
I'm Brian Nichols.
and this is our presentation.
Our topic: using a laser to measure the speed of light in different ratios of gelatin, while comparing it to the constant speed of light through a vacuum.
Alright, our question was, how does composition of the gelatin influence the speed of light?
Okay, so the importance of our experiment is it describes a simple way to manipulate the speed of light. Also, I want you guys to describe this picture for me. So will someone raise their hand and describe this picture?
Refraction.
Refraction, that's right. Okay, so if you look, you can see that the straw comes in at this angle, but you see it over here, and it's at a completely different angle, and that's due to refraction. This is important because it separates our perspective and reality, and oftentimes a lot of us are teenagers in here, so we oftentimes mix up reality from our perspective. So.
Okay. Now, before we get into the experiment, we have to know a little bit with what we're dealing with. And since this is physics, gosh, why do I have to do physics? So, in physics and math and algebra, well, algebra is math, so yeah. We have to know, these are our two main laws, or formulas that we have to use. The first one is Snell's law, and the other one is index of refraction. And further in this presentation, we will explain those to you more in depth.
Alright, the materials that we use 4 plastic containers, 4 packages of clear, non-flavored gelatin, pencil and paper, a protractor, a spoon, a laser pointer, and water.
And as in most non-case study experiments, we have variables. And we have 3 types of variables in our experiment: independent, dependent, and control. For our independent variable was gelatin consistency, and dependent variable was the speed of light and the angle of refraction. The control variables was the laser and the angle of the laser's position, which is the incidence angle.
So to walk you through our experiment step by step, of course we started to gather materials. After that, we prepared the gelatin, and once we had those in the container, we labeled those thick or thin so we wouldn't get confused. And after that, for each container, we pointed the laser at the container at a 45-degree angle, which is our angle of incidence.
Okay, step 5 was to measure each angle of refraction, and that's the angle that goes through the gelatin. Step 6 was to use the index of refraction to find the refractive index for air, which is a constant of 1. And the last step was to plug in all of our information into a specific equation called Snell's law, and then we had to calculate the speed of light for each type of gelatin. So we took our index of refraction for the gelatin and divided that by the speed of light through a vacuum, which ultimately gave us the speed of light for each type of gelatin. Okay, so now we're going to break down exactly how we prepared the gelatin. We had 4 different trials, and for 2 of the trials we made a thicker gelatin, and for the other 2 it was a thinner gelatin. To create the thicker gelatin, we used 1 package of gelatin mix and half a cup of boiling water and half a cup of cold water. And for the thinner gelatin, we used 1 package of gelatin and a cup of cold water and a cup of boiling water.
Now, some of you may be asking yourself, why are they doing this? Why are they not doing this? And just to go back to the importance a little bit, we're doing this because perspective and science are 2 different things. Perspective is what we think, and science is what is proven. As in, a theory is an explanation of something that can also be proven, but yet it's not proven, if you understand what I mean. So in Snell's law, it is the formula used to describe the relationship between the angles of incidence and refraction when light passes through particular mediums. In our case, the thin and thick gelatin and air. And this is our formula for Snell's law.
Okay, so when you take the sine of the angle of refraction, which varies for each trial because that's the angle within the gelatin, and you multiply that by the index of refraction for gelatin, which is our unknown and what we had to solve for, that equals the sine of the angle of incidence, which was held constant throughout each of the trials at a 45-degree angle, and you multiply that by the index of refraction for air, which is also a constant of 1 again.
Lucky for you guys, we put in the work, so now you can just throw that left side equation out of your way. And once we rearranged the equation, it was more like index of refraction for gelatin is equal to sine angle of incidence multiplied by the index of refraction for air divided by sine angle of refraction.
And we had had to do this because we had to solve for the unknown, which again was the index of refraction for gelatin.
So we had to use algebra.
Okay, and this is kind of a picture of what it would look like. Down here represents the air, the blue area, and the top represents the gelatin. This midline right here, the horizontal line, is what's called the interface. And that purple line right here is what's called the normal. It's just an invisible line. And the arrows pointing here, that is the angle of incidence, and the angle pointing out is the angle of refraction.
Okay, now here's our results after we've tested our hypothesis or our question. For the speed of light through the thin gelatin was approximately 224 million meters per second. And as we see that the difference from the constant speed of light through air is 75 million meters per second. And for our second trial, we got the same one since the index of refraction was the same. Also, the angle of refraction was 20 degrees. So each one, they remained constant for these two trials.
Our results for the thicker gelatin, also known as G2, for the speed of light in trial 1, it was roughly 210 million meters per second, and the difference was roughly 88 million meters per second. And that differed from trial 2 just a little bit. It was also near 210 million meters per second, and the difference is also near 90 million meters per second.
Now, after we got our results, we plugged it into our graph. And here we have the index of refraction, and gelatin 1 and the two trials, and gelatin 2 and the two trials. And here's our graph. And so we wouldn't have so many numbers and significant digits. We just decided to label it 10 to the 6th power meters per second. And here, SOL, which is speed of light, we see that it's approximately 299 million meters per second. And you can see how different the gelatin 1, trial 1, and trial 2 is different, about 80 million meters per second slower than the speed of light. And Veronica, in the next slide, will explain to you how gelatin 2, trial 1, and 2 are different from these three.
Alright, this is a closer look to the graph for the thicker gelatin. This graph is closer to numbers, so you can tell that there is an actual difference between gelatin, thicker gelatin, trial 1, and the other thicker gelatin, trial 2.
Because as, can you go back to the next slide, or the last slide, yes. As you see these two, do you see how relatively close they are? So, back to the next one. We just made the scale a little more broader so you can see the actual difference, as we couldn't see in the other one.
So, to wrap things up, our evidence supports our hypothesis since after experimental research was performed, and we resulted in constant speed of light equals the fastest speed. The thicker gelatin showed the slowest speed of light, while the thin gelatin had the medium speed of light.
We'd like to thank Mrs. Morgan, Ms. Rogers, Ms. Santiago, our mentor, Mr. Lockard, the UVMS and WSU staff, and our lovely audience.
Yes.
Did you account for what effect the container might have?
In our experiment, we didn't explain to you. We didn't use a container. We molded out the gelatin from the container and we put it on wax paper. So it was, yeah. Any other questions, comments? No?
Thank you.
Oh, yes. One last one. I can't hear you.
Other than simplicity, was there any other significance to using gelatin instead of water?
Yes, because as we explained how we had thin and different,
We wanted to measure how consistency would change, so like if the density would affect the speed of light.